Conservation of energy is probably the most important idea in all of science. Energy can neither be created nor destroyed. It can only be changed from one form to another. For our purposes, we'll say that the total energy of a system remains constant, as long as we account for the work done on or by the system. In equation form, we can write simply that the initial energy plus the work done equals the final energy. The way we approach a conservation of energy problem depends on how we define the system. In this example, an apple falls from rest toward the surface of Earth. Here's what we end up with if we define the system as being just the apple itself. The initial energy is 0. There's no gravitational potential energy if there's no gravitational field within the system. There's also no kinetic energy originally or spring potential energy. The gravitational field of the Earth still exists, it just exists outside of the system. That external gravitational field is able to exert a force on the apple, causing it to move with some displacement. After it has fallen for a while, it does end up with kinetic energy. The apple is moving. The work done by the gravitational field is the force of gravity times the displacement, which is the change in height of the apple. And of course, kinetic energy is 1/2 mv squared. Let's take a look at this with a different definition of our system and see that we end up with the same final equation. Let's define the system as including the apple and the Earth. This time, the apple does start with gravitational potential energy because the Earth is part of the system and so is its gravitational field. In this case, there are no forces external to the system to do any work on the apple. Therefore, the work is 0. And, as before, the apple is moving after it has fallen for a while, and so it ends up with some kinetic energy. The equation for gravitational potential energy, remember, is mg delta h, or Fg delta h, and the kinetic energy formula is 1/2 mv squared. I want you to notice that as long as we're careful, it doesn't matter how we define our system. We should end up with the same result either way. We always want to approach a problem with some sort of strategy in mind. In some more straightforward problems, we use the guess method, and we start by listing our givens and the unknown. With force problems, we often draw a free body diagram. One strategy for setting up a conservation of energy problem is to sketch energy bar charts, also known as an LOL diagram. On the left, we have a quasi-quantitative bar chart showing the relative amounts of kinetic energy, gravitational potential energy, and spring potential energy. If there were other forms of energy involved in a problem, we can include those. If we know that, let's say, there's no springs in the problem we're solving, we could leave out the spring potential energy. Use this however it works for you. What we also do, inside a circle to the right, is define what objects belong in our system. This will give us an idea of what the sources of work done on or by the system can be. If there's any positive work done on the system, we can draw an arrow pointing to the system to represent that. We can even incorporate the quasi-quantitative nature of this diagram by essentially making the arrow a bar that could be added to or subtracted from one of our bar charts. If there's any negative work done on the system, we can draw an arrow pointing away. On the right, we'll draw a new set of energy bar charts, and we'll adjust the size of each bar based on our understanding of what happened in the problem. In this case, the system gained kinetic energy and lost some spring potential energy. This will make a lot more sense if we look at an example. Mario is propelled upward by a trampoline. Once again, I want to look at this problem with many different definitions of the system, just to see that we get the same result no matter what, as long as we're careful. First, let's say that the system is just Mario himself. He's not moving, so there's no kinetic energy. Within the system, there's no gravitational field, so there's no gravitational potential energy. And within the system, there's no spring or trampoline, so there's no elastic potential energy. When the trampoline releases, it does positive work on the system. We know this work is positive because Mario's displacement is upward, and the force from the trampoline is also upward. As Mario gets to his highest point, there's negative work from gravity. We know this work is negative because, again, this whole time Mario's displacement is upward, but the force of gravity is downward. Now let's take a look at the bar charts for each of these energies at the end. Well, at his highest point, he's not moving, so there's no kinetic energy. And once again, there's no gravitational field or trampoline included in the system, so there can be no gravitational potential energy or spring potential energy. From here, we can write a conservation of energy equation, which we can then plug in some given values and solve for whatever our unknown is. Now that we understand what's true about the energies and the work done in this problem, we can set up a conservation of energy equation. There's zero energy to begin with, and then there's a combination of positive work from the trampoline and negative work from gravity. We also know that we end up with zero energy in the system. We can rearrange this to simply say that the work done from the trampoline is equal to the work done by gravity. We know the equations for each of these things. The work done by the trampoline, which we'll assume is basically like a big spring, is 1/2 kx squared, and the work done by gravity is the force of gravity times the change in the height. Let's look at this problem again, but this time we'll include the Earth as well as Mario in the system. In the beginning, Mario is at rest. He does exist in the gravitational field of the Earth, which is part of the system this time, but he's at his lowest position, which is where the gravitational potential energy is zero. Since the trampoline is not part of the system, there's no elastic potential energy. When he jumps, there's still that positive work from the trampoline, but since the Earth and its gravitational field is now part of our system, there's no negative work done on the system as a whole because of gravity. Instead, we'll say that the system ends up with some gravitational potential energy because Mario has increased his height in this gravitational field. When we write the conservation of energy equation for this problem, we see that we once again started with zero energy, but this time there's only work from the trampoline. At the end, the system has some gravitational potential energy. The work done by the trampoline is 1/2 kx squared, and the gravitational potential energy is Fg times delta H. Notice it's the same equation we had before. Let's look at it again. This time, the system is Mario and the trampoline, but not the Earth. Since the trampoline is compressed at the beginning, there is some elastic potential energy. Since the trampoline is part of the system this time, when Mario jumps, we won't say that there's any work done on the system. The trampoline is in the system, so it can't do work on the system. Since the Earth and its gravitational field is outside of the system this time, we'll say that gravity does negative work on the system. At the end, Mario is not moving, so there's no kinetic energy. There's no gravitational field in our system, so there's no gravitational potential energy. And the trampoline is no longer compressed, so there's no longer any elastic potential energy. When we write our conservation of energy equation, we get the original elastic potential energy plus the negative work done by gravity equals zero energy at the end. We can rearrange this to say that the elastic potential energy is equal to the work done by gravity. This gives us, once again, 1/2 kx squared equals Fg delta H. One more time, and then we're done, I promise. This time, the system is Mario, the trampoline, and Earth. In the beginning, the trampoline is compressed, so there's some elastic potential energy. Then Mario jumps. There's nothing outside of the system to do any positive or negative work on the system. At the end, Mario is not moving, so there's no kinetic energy. He has increased his height in the gravitational field, so there's gravitational potential energy. And of course, the trampoline is not compressed anymore, so there's no more elastic potential energy. Here's what our conservation of energy equation looks like for this problem. We start with elastic potential energy, and we add no work, positive or negative. We end up with gravitational potential energy. This gives us, you guessed it, 1/2 kx squared equals Fg delta H. Let's take a look at another problem, this time quantitatively, and I promise we'll only do it one time. A 60,000 kilogram airplane flying at 8,000 meters accelerates from 200 meters per second to 250 meters per second while climbing to an altitude of 10,000 meters. How much work was done by the airplane's engines? Here's how we'll define our system. We'll include the airplane, but not the chemical potential energy of the fuel, and we'll include the Earth. At the beginning, the airplane was moving, so it had some kinetic energy, and it was 8,000 meters above the surface of the Earth, so it had lots of gravitational potential energy. While it was accelerating and gaining altitude, there was positive work done from the engines. Afterward, there was still kinetic and gravitational potential energy. There was just a little bit more of each of them. Here's what we'll write for our conservation of energy equation. We started out with kinetic energy and gravitational potential energy, and then there was some positive work done. All of that is on the left. Afterward, there was still some kinetic energy, and there was still gravitational potential energy. If we rearrange this to solve for W and put like terms together, we can get W equals the difference between the final and initial kinetic energy plus the difference between the final and initial gravitational potential energy. We can rewrite this as W equals delta KE plus delta PE. If we substitute in the equations for those changes of energy, we get W equals 1/2 m times v squared minus u squared plus mg delta H. I'm not going to show the substitution and all of the arithmetic here, but I encourage you to give it a try. I found that the work done by the airplane's engines was 1.85 times 10 to the 9 joules, which we could also call 1.85 gigajoules. Finally, let's talk about efficiency. It would be nice if all the work done by a person, or a machine, could end up as the desired form or forms of energy. This, however, would require 100% efficiency, which just isn't possible. There's always some energy loss involved. This could be due to friction, which creates heat, or sound, or light, or something else. And of course, this energy isn't lost, it's just not in the form that we might desire. We define efficiency as the useful work out divided by the total work in. Or, if we're interested in the rate at which the work is being done, we can say that efficiency is the useful power out divided by the total power in. Let's take a look at an example of efficiency. In the previous problem, we found that the useful work out from the airplane's engines was 1.85 gigajoules. A modern commercial passenger jet aircraft has an overall efficiency of about 40%, and the energy density of jet fuel is 34.7 megajoules per liter. First, what was the total work in? And second, how many liters of jet fuel was required to accelerate and increase the altitude of the airplane? Well, efficiency is useful work out divided by total work in. We have to represent efficiency in decimal form, so we'll say the efficiency is 0.4. This equals the useful work out of 1.85 times 10 to the 9 joules, and that's divided by the total work in. Using this equation, we can find that the total work in must have been 4.625 times 10 to the 9 joules. The last question is kind of just for fun. How many liters of fuel do we need to add up to 4.625 times 10 to the 9 joules if each liter has 34.7 megajoules of energy in it? We can simply take the total energy in and divide it by the energy density of the fuel. 34.7 megajoules per liter is 34.7 times 10 to the 6 joules per liter. we can find that it took 133.3 liters of jet fuel to accelerate the airplane and increase its altitude.